Hello everyone, I am Mohammad Masdur Rahman from Institute of Information Technology, University of Dhaka, Bangladesh, and author of the paper entitled An Empirical Study on the Occurrences of Codismals in Open Source and Industrial Projects. These are the outlines that I will discuss today in this presentation. Background of the study. Codismal. Codismal is an important design aspect in software engineering domain. Basically, it is a negative aspect of software design. Codismals are not programming errors or bugs, but these are the symptoms that affect code comprehensibility and maintainability. However, Martin Fowler, father of codismals, defined 22 types of codismals. For example, long method, complex class, long parameter list, etc. We actually have two types of software development environment: industrial, also known as in-house, and open source. Industrial software. A software is developed in this environment having specific team members and structures in the same environment, release and budget constraints, coding rules and conventions, etc. On the other hand, open source software. A software is developed in this environment where developers sit geographically different locations. It exists different mindsets and goals of the developers, no hard and fast rules, little release and budget constraints, etc. Problem specification. There exist a lot number of codismals in the literature. Many of those occur frequently and many are not. So the problem is which codismals occur frequently in both types of software individually and which are not. As there exist differences between the two development environmental processes, we actually want to explore the differences between the occurrences of codismals in open source and industrial projects. Motivation of the research. Remembering a long list of codismals while developing system is difficult for developers. This work actually provides insights about the most frequently occurring codismals in both open source and industrial projects. Again, short frequent list of codismals make developer aware of writing smell-free code or at least minimizing the occurrences of smells, right? Also, it helps researchers to innovate refactoring tools for the smells on priority basis. Next, existing literature. Most of the works have covered the detection of the code smells. For example, JDeodorant, that is an Eclipse plugin which identifies 6 types of code smell. Another tool, Decode, it detects 18 types of code smells using rule card. Several works have performed impact analysis of code smells on maintainability. For example, Yamashita et al. Showed inter-smell relationships considering couple smell using 3 projects. Another study, Palamba et al. Analyzed the co-occurrences of code smells using large-scale software projects. Research problem. However, there is a noticeable lack of knowledge about the occurrences of code smells in industrial systems. Moreover, to the best of our knowledge, there exists no such empirical work regarding the comparative analysis of code smell occurrences between open source and industrial systems. Basically, the research methodology consists of 3 steps: formulating research goal, data collections, and detection of code smells. Formulating research goal. Here we actually identify 3 research questions. RQ1. What types of code smells do occur in open source and industrial systems respectively? RQ2. Which types of code smell do frequently occur in open source and industrial systems? RQ3. Are there any differences between the occurrences of code smells in industrial and open source systems? Second step, data collection. The study consists of software systems from both open source and industrial projects. We have analyzed 40 large-scale Java systems as our dataset, where 25 are well-known open source systems and 15 are industrial systems. The description of the dataset are shown in this table. Third step, detection of code smell. To carry out the investigation, a list of 18 code smell has been selected using a tool named Decor because it actually identifies a large number of codecimal, 18 codecimal, and it shows higher accuracy in the previous study. So this table actually shows the whole result of the study. First column shows the list of 18 codecimals. The next columns shows total decimal frequency, average decimal frequency, sphericity, and three ISF, that means inverse decimal frequency score based on log, norm, and knob. Log, lines of code, number of method, and number of class. So it has actually two parts: industrial systems and open source system. And the final column consists of p-value for the comparative analysis. We actually discuss the result in the following slides. RQ1. According to the result of the study as shown in the table, out of the 18 codecimals, 6 decimals have not been found in both open source and industrial systems. These rest 12 decimals have been seen present in both categories of the system with different extents or frequencies. The findings indicate that developers should be more careful on these issues and researchers should give more emphasis on the improvement and invention of the detection and reflection techniques for the issues. RQ2, frequent codecimals. To get an idea about the extent of the presence of the isthmus, the answer of RQ2 describes the frequency of the occurrences of codecimals from different granular levels. For this, we define the following three metrics: sphericity, average frequency, and inverse decimal frequency. Sphericity is a metric that defines the existence of a decimal with respect to the total number of systems. Higher value of the metric for a decimal indicates higher number of systems contain the decimals. The maximum value will be 1 if all the systems contain the decimal, and it will be 0 if none of the systems contain it. Average frequency is the average number of the occurrences of each codecimal per project. Inverse decimal frequency is the average number of the metric value for like log, norm, or knock for which a particular codecimal occurs. The metric is calculated using the following equation. That means metric value divided by decimal count. Figure 1, the horizontal axis contains the decimal names and the vertical axis contains the sphericity score. Blue colors for in-house or industrial projects, orange are for open source projects, right? From this figure, we actually found that complex class and long method occurs in every project, both industry and open source systems, because these values are 1, right? Third one, long parameter list, it actually occurs in in every project in open source, but only 0.93 for in-house projects. If we see carefully that the sphericity of the codecimals are comparatively less in the industrial system than open source one, right? Figure 2 depicts the average frequency of the occurrences of each codecimal per industry and per open source systems. Like sphericity, long method tops with highest frequency, then complex class, the second highest, and long parameter list will be the third one. Here we can find that the other issues are less frequent. If we see carefully here that the average frequency seems higher in the industrial system than open source systems. RQ2, frequent codecimals based on ISF score. Figure 3, 4, 5 illustrates the score of ISF based on log, norm, and knock score. So the lower the value of the metric for a particular smell indicates the more frequent of the occurrences of the smell. And here we can see that long method, complex class, long parameter list are the smell that contains lower ISF score, and these are true for every figure in this slide. And the higher value means these are less frequent. So for example, a long method, for both in-house and open source project. After every 670 lines, a long method code smell will occur. After every 41 method and 45 method for in-house and open source respectively, a long method code smell will occur. And for after 6 and 7 classes respectively, a long method code smell will occur. If we see the higher value of a code smell like speculative generality, it actually has a large number lines of code that a is a SG, that means speculative generality code smell will occur. So these are less frequent code smells, right? So the severity of the issues is more in open source systems than industrial systems. Conversely, the issues are more frequent in industrial systems than the open source systems. These research questions aims to identify whether the occurrences of code issues differ between the open source and industrial systems. A statistical hypothesis testing one-tailed t-test with 5% level of significance has been conducted, where the null hypothesis is there is no difference between the occurrences of a particular code smell in open source and industrial system. So the alternative hypothesis is the occurrences of a particular smell in open source system is greater than in industrial systems, right? According to the p-value given in the previous table, the alternative hypothesis has been rejected for all the smell except base class should be abstract and refused parent because in favor of the null hypothesis. So conclusion, the study attempts to identify the most frequent occurring code smells in both types of software systems, open source and industrial. It is interesting that 6 out of the 18 smells have not been occurred in any systems, whereas 3 smells, long method, complex class, long parameter list have been the most frequent ones in both types of systems. The inclusion of the industrial systems along with the open source one makes the study more interesting in a sense that most of the smell occurrences are similar to both types of the systems. Moreover, we have discussed the smell frequency using two newly defined metrics in this work, Spirity and ISF score, which provide useful insights in this research domain. Therefore, these findings will assist developers to reduce the smells while developing systems and researchers to innovate the smell refactoring techniques from the viewpoint of frequency analysis. Our future plan is to find the reasoning of why the smell occur frequently while the others do not. Here are some references. Uh, Thank you, everyone.